Now let's talk about polar arc length. And there are a couple different ways of figuring out the equation for the arc length of a polar graph, but I'm going to kind of go over a generalized arc length and then kind of use it to figure out what the polar arc length equation is. So if you guys remember back a couple units ago, you guys had this equation for the arc length of this function, y equals f of x. It's just the integral of the square root of 1 plus the derivative squared dx. So where that's coming from is the parametric equation, which is, if we want to write this as a parametric equation, we'd have y equals f of t, and then x equals t. And then the definition of arc length says that you're pretty much taking the integral of the square root of the derivative of the first equation squared plus the derivative of the second equation squared. And notice that if we take the, well, let me write that out first. So we're taking the integral from some t1 to t2. So we're taking the derivative of x squared, so dx with respect to t squared, and we're adding that to dy dt squared. Notice that dx dt, the derivative of x with respect to t, that's just 1, so we're left with the integral from t1 to t2 of 1 plus dy dt squared dt. And now looking back, we can notice that the derivative of y over here with respect to t is the same as the derivative with respect to x of this equation right here. So that's where you can come up with this. We're just changing these t's into x's pretty much, since they're equivalent. So that's kind of how I like to think about arc length. And from that, we can figure out what the polar arc length is. So let's go ahead and do that. So once again, remember, we're saying that the arc length is just the integral of the square root of the sum of the squares of each part of the derivative of the parametric equations. And that sounds long and messy, but it kind of turns out to be nice, especially with polars. So we already know the parametric equation for polars. We know that y is equal to r sine theta, and x is equal to r cosine theta. And from figuring out tangents, we had to find the derivative of y and the derivative of x. So dy d theta is equal to, and that just involved the product rule. So dy d theta is just the r d theta sine theta plus r cosine theta, and likewise dx d theta is simply dr d theta cosine theta minus r sine theta. So now what we have to do is, since we're looking for the square root of the derivative squared in arc length, because remember we're taking the square of the derivatives of each part of the parametric, let's solve for dy d theta squared plus dx d theta squared. So, and this is kind of where we get a bit messy with the algebra, but it all turns out pretty nice. So we're pretty much solving for the square root right here. So dx d theta squared. Let's first just write it out. Dr d theta cosine theta minus r sine theta squared plus dr d theta sine theta plus r cosine theta squared. Multiply it out, do some algebra. This turns out to be, let's see, dr d theta squared cosine squared theta. We get 2 times the product of the two different terms, so minus 2 r dr d theta cosine theta sine theta. And then the last term squared, we get a positive r squared sine squared theta. And we need to add to that, I'm going to write it down here since it's going to be pretty long. Well, first term squared, dr d theta squared times sine squared theta plus 2 times the product. So we get an r dr d theta cosine theta sine theta plus an r squared cosine squared theta. So let's see if let's see how this looks once we clean it up. Well, we have this negative 2r dr d theta cosine sine theta, and we have this positive 2r dr d theta cosine sine theta. So those are going to cancel out, so that's pretty nice. And let's kind of gather up these dr d theta squareds. So we have a dr d theta squared, so we have a cosine squared theta, and we have a sine squared theta. Sorry. We have a cosine squared theta, and we have a sine squared theta. And now let's look at this r squared. So we have an r squared here and an r squared here. And once again, we have a sine squared theta and a cosine squared theta. And look at that. We know what cosine squared plus sine squared is. That's just 1. And we're left with dr d theta squared times 1. I'm not going to write that. Plus r squared times 1. So what does that tell us? That the arc length, I'm going to call that L, is just the integral. Well, our variable is theta, so from some theta 1 to some other theta 2 of the square root of dx d theta squared plus dy d theta squared, which comes out to be dr d theta squared plus r squared. All that with respect to theta. So pretty much what we're doing is we're going to take the integral from some angle to another angle of the square root of the derivative of our function plus our function squared. And in the next videos, we'll go over some practice problems. This video, we just kind of went over the general equation. So this is definitely an equation that you want to memorize, since you don't want to be doing all this math and deriving it during a test. So memorize that equation, and then we'll go over some practice problems later.